Start now. So as for our last talk, it's a great pleasure to have Hassaan Saleem from Albany. He will be talking about constraining boundary conditions in non-rational conformorphic theories. Please.
Thank you. Okay, so first of all, thank you to the organizers of this conference to let me present my work in this conference. So we're going to talk about non-rational CFTs, and this is actually the plan. Let me just go through this. So the thing is that there are a lot of methods that we have for constraining boundary conditions in rational CFTs, but those methods don't always transform to non-rational CFTs. So what we are trying to do here is that we're trying to study the distinctions that these methods have when it comes to rational and irrational or non-rational CFTs. And as a lab to study these distinctions, we're going to talk about the compact free boson. Okay. So this is a small review of what boundary states are and how they are constructed. So as you know that if you have a two-dimensional CFT, you can talk about the boundary conditions in terms of boundary states, and we do know that a CFT contains primary fields when it has primary states, right? And if you want to construct a boundary state, which is referred to as BA here, B alpha here, you need to construct it in terms of some basis states which are called Ishibashi states, and Ishibashi states correspond to zero spin primary states. Okay. So these A alpha i's are just coefficients that you have for different boundary states. Okay. So for the compact free boson, we apply this identification on the target space, which is just one-dimensional in our case. And in this talk, we will take the self-dual radius alpha prime to be equal to 1. So this is the classical solution for the compact free boson, and it can be written as as a holomorphic part and as an anti-holomorphic part. So I'm sure you already know this, so I think I don't need to go through this. Okay, now let's talk about what Ishibashi states do you have in the compact free boson case. So you have two types of primary fields. One type of primary field is something like this, and these are the corresponding conformal weights, right? Now, as I said in the earlier slide, that Ishibashi states correspond to spin 0 primary states. So spin 0 primary states require m to be 0 or n to be 0, which means that the Ishibashi states are either these or these. Okay. So the other type of primary fields that we have can be written something like this, right? And I have written these primary states such that their conformal weights agree on the holomorphic and anti-holomorphic sides. And since they are already spin 0 because their conformal weights match, so the Ishibashi states can just be written like that. Okay. So what are the boundary states for free boson, compact free boson? So two boundary states are very well known: the Dirichlet state and the Neumann state. So this is the Dirichlet state, and you can see that this particular boundary state does not make use of these Ishibashi states 0m, and this is the Neumann state, and this does not make use of this Ishibashi state n0, but both of them make use of these JJ states. Okay. Okay, so there is another boundary state that was proposed by Friedan and then worked out by Janik in 2001. And in these boundary states, you can see that only the JJ states appear. And these coefficients are nothing but the Legendre polynomials. And these polynomials were determined by Janik in 2001. Now, the thing is that we are going to talk about the problems with these FJ states, which is just Friedan-Janik states. Now, some problems are already well known in the community. So, for example, this problem was already addressed by Janik in his 2001 paper. The thing is that when you calculate the overlap of two different Friedan, or they don't need to be different, I mean they can be anything. So, two different Friedan boundary states, it turns out that their open string spectrum is continuous. It's not discrete. Now, what's the problem with that? The problem is that if the open string spectrum is continuous, you cannot use Cardy condition to figure out this normalization constant. So this is the normalization constant, and we will talk about that later as well. Now, the thing is that Friedan didn't write this overlap in this form, but we actually wrote it in this form, and we also figured out what this density of states function is. I will talk about that later. But the problem is that the Friedan-Janik states have a continuous spectrum, and that's a big problem. If you compare that to Dirichlet and Neumann boundary states, you can see that their open string spectra are discrete, right? And because of this fact, you can use Cardi condition to figure out the normalization constants there. For example, if you go back and see, we do have explicit expressions for the normalization constants here. Okay. Now, another problem that we worked on is that Friedan-Janisch states don't satisfy the cluster condition. Now, this is one of the consistency conditions that you need to satisfy if you want a good boundary condition. What Janisch did in his 2001 paper is that he checked this cluster condition for I and J being the JJ states. Now, if I describe briefly, these B coefficients are nothing but ratio of A coefficients that I had in the first slide, and the ratio of these A coefficients with the A coefficient for the case when I equals 0, which means that the identity operator, right? And these M coefficients that you have here are nothing but the contraction of the OPE coefficients and the fusion matrices, right? So what Janisch did was that he did check the cluster condition for I and J when these are corresponding to the JJ states, but he didn't check the other cases. For example, he didn't check the case when I and J are N0 or M0 and so on. So what we did is that we checked the exact same thing, but it turns out that it's much more convenient if you first define the new Ishibashi states, which are something like these. The advantage of these Ishibashi states is that if you write the Dirichlet and Neumann states in terms of these Ishibashi states, then the coefficients become real. You don't have to deal with complex numbers anymore. Okay, so if you do that, then it turns out that if you can use the fact that Dirichlet and Neumann states do satisfy the cluster condition, and that particular fact puts some constraints on these M coefficients, and the constraints come in this form, that these particular M coefficients should sum up to give you 1. Okay, so this should be true because we do know that the Dirichlet and Neumann states do satisfy the cluster condition. Now we can do the same thing for Friedan-Janisch states, and let's see what happens. So if you do the same thing for Friedan-Janisch states, you get these constraints. But the thing is that we do know that the Legendre polynomials are orthogonal, which means that we can use this orthogonality to derive the fact that each individual M coefficient should be 0. But you can see that this is an inconsistency. If you look at these equations and then look at this equation, you can see that this is not consistent with each other, because these M coefficients, if they are 0, they cannot sum to give you 1. So it means that the Friedan-Janisch states don't satisfy the cluster condition. Okay. Now there's a third problem with these states as well. And to talk about that particular problem, I will briefly need to talk about what is the G function. Most probably you all already know that, but let me still go through that. So if you consider a partition function of a CFT on a cylinder with boundary conditions alpha and beta on its two boundaries, and let the length of the cylinder be small l and its circumference be capital L, then this is the partition function. Okay. Now let's talk about the limit in which the cylinder becomes long, which means that small l goes to infinity. I mean that small l becomes much bigger than capital L. So if you take that limit, the partition function has this particular form, where this E0 is the smallest energy state that you have in the theory. Now, these factors that are appearing here are called the G functions of the boundary state. So you have G alpha and G beta. This corresponds to the boundary states that you have here and here. Now, this was actually introduced by Affleck and Ludwig, and this is sometimes also called the Affleck-Ludwig boundary entropy. So you can think of the G function as the boundary entropy of a boundary state. Okay. So, this is the conceptual underpinning of G function. Now, what's the problem with Friedan-Janisch boundary states? The problem is that you can calculate the G function for Neumann states, for the Dirichlet states, and for the Friedan states as well. And if you remember, I told you that the Friedan states have an undetermined normalization constant. So it turns out that, so you can get very reasonable expressions for the G function of Neumann state, for the Dirichlet state. But for the Friedan state, since you don't know the normalization constant, you just get the fact that, the G function has to be equal to the normalization constant, whatever it is. So this is not a problem. The problem starts later. The problem starts when you start talking about Gaberdiel-Recknagel states. Now, these states were not included in the states that I talked about earlier. And the reason is that these states are not realized at every particular radius. these states are only realized when you have a radius which is a rational multiple of the self-dual radius. And you don't need to know the exact form of these states. The only fact that you need to know is that these states are labeled by elements of the SU2 group. And secondly, of course, these are also labeled by these integers m and n, because these integers actually specify the radius. Okay, now what you can do is that you can calculate the g function of these boundary states, and you get something like this. Okay. Now, the fact that we're going to use is that if you want to approximate any real number r, you can do it by a sequence of rational numbers. So, for any real r, there exist sequences m and n such that this particular sequence converges to r. But if r is rational, these sequences converge. It is easy to see. But that's not the case if r is irrational. If r is irrational, m's will become bigger and bigger and bigger, and n's will become bigger and bigger and bigger. So these sequences diverge. Okay. Another effect that I'm going to use is this. So in their paper, Recknagel and Gabriel showed that if you take their boundary states, and if you take the limit when r is an irrational number, then their states, which is this, become Friedan states, right? So you can see that m and n going to infinity means r becoming irrational because of this fact. Okay, and what is the correspondence between the boundary states? Well, so since Recknagel-Gabriel boundary states were labeled by G, which is a member of SU2, so you can write a general SU2 element like that with A and B being complex numbers. You can write down the correspondence between A and theta, which actually labels the Friedan boundary states. Okay. Now, here's the problem. The problem is that if you calculate the G function for the Friedan state and the G function for the Recknagel-Gabriel states in the limit when n and m goes to infinity, the G functions should match. But this limit says that m and n go to infinity, which means that this thing should go to infinity, and in turn it means that the undetermined normalization constant for the Friedan-Janic state is actually infinite, and this makes no sense. So therefore this is another problem that the Friedan-Janic states have. Okay, my last topic is about the density of states that I talked about earlier. So I mentioned earlier that if you try to calculate the overlap of two Friedan-Janic boundary states, the spectrum, open string spectrum, is continuous. Okay, it's continuous, but these density of states, is something that are not this density of states function is not calculated yet. So you can calculate it. I mean, it's a long calculation. It's not hard, but it's a long calculation. You need to have three kinds of intervals, and then you can specify the boundary of states function as a function over these three different kinds of intervals. And you can see that each of these intervals has this subscript n, which means that for each integer you have three different kind of regions. So the expression is messy, but you can derive it. So this is the expression where this k is the elliptic integral of the first kind. So you can derive the expression. At the end, I will just show you some special cases for these density of states. So for generic theta values, so for example, here we have theta equals pi over 2 and 2 pi over 5, pi over 5 and 2 pi over 5. The density of states has these discontinuities. Now this is another undesirable feature for density of states. So you can think of it as another problem with the Friedan-Janic states, but this is not a concrete problem. But okay, you can say that okay, it's some problem, but not a concrete problem. Another case is when theta 1 and theta 2 are equal. Now you can see that the discontinuities vanish, but still you have this weird looking behavior. And it turns out that you can write down the case when these are equal, but both of them tend to 0, as a very explicit sum of a discrete part and a continuous part. So you can write it like this. But it turns out that this discrete part, if you integrate it over all the conformal weights, it gives you 0. So at the end of the day, the whole contribution is coming from the continuous part. And the last case is this case where the theta 1 and theta 2 add up to give you pi. Now in this case, you can see that a sum of delta function type of structure is appearing. As I told you earlier, that for Dirichlet and Neumann states, the spectrum is discrete, which means that in those cases you had a sum of delta functions. So that particular structure, it's the last slide. So that particular structure is realized when you have theta 1 and theta 2 adding up to pi. So actually, accidentally, I submitted the version of the slide which doesn't have the future directions. So I'm just going to tell you the future direction. It's only one. So we are trying to see if we can get Friedan states in the case when you have free boson, compact free boson orbifolds, and see if we can rule them out by similar methods as well. So that's the only future direction that we have in this particular work. So thank you for listening.
Thank you. Questions?
I can understand this is the last talk anyway. So.
So in this computation where you derive the normalization factor as a limit from some going from some rational function to some rational number to some irrational number.
So sorry, I can't understand what you're saying.
So in the computation where you derive the normalization factor in this way by going from some rational number to something irrational.
No, it's not going from rational to irrational. What I was actually quoting a fact. I was saying that you take any rational number, any real number, then you can always find a sequence of m's and n's such that m over n will tend to that real number.
Yeah, sure, but is it clear that this kind of limit has to exist in this move?
Sorry, I didn't understand.
Is it clear that this kind of limit has to exist?
Yes. So for any real number r, you can find such a sequence. It's the other way around, actually.
Yeah, for the number, sure, but for the normalization factor.
No, wait. So, okay, I use the sequence thing for the radius, right? So the normalization factor appears when you have the irrational radius limit, right? Because I want to relate the Gabriel states and the Friedan states, and Gabriel and Recknagel showed that this relation exists only in the limit when r is an irrational number. So I'm not when I'm talking about the sequences, I'm not talking about the the normalization constant. I'm talking about the radius, and radius is just a number.
Other questions? If not, let's thank the speaker again.